All right, welcome back. Still on linear approximation. So let's delve into more questions on linear approximation for you to consolidate your knowledge. All right. The very first question we have here is for us to find the very first five terms of this particular binomial expression. All right. So we have 1 minus 2x raised to the power of 11. Of course, I will not be doing so much of the solving because I'm sure we already know how to arrive at those values. So I'll just be giving you the values we got. So what we got here is 1 minus 22x plus 220 x squared minus 1320 x cubed and then plus 5280 x raised to the power of 4. Right? So this is the very first five terms. You can confirm that this is 1, 2, 3, 4, 5. So obviously, you understand the whole concept of binomial expansion. If you don't understand how to go about expanding an expression, you can go to our previous video. You would get the real understanding on that. Now, this is for when k, our incremental value, k being from 0 to n. Here, our n is 11. So when k was 0, we got 1. When k was 1, we got this minus 22x. When k was 2, we got 220x squared. When k was 3, and this was when k was 4. All right, so this is our very first five terms. And of course, I'm sure you should be able to infer already that wherever, for you to know the number of terms in a binomial expansion, whatever the power was, this is 11. Just add 1 to that power. So in this case, we're going to expand this completely. We're going to be having a total of 12 terms. So if we had a power of 10, we're going to be having a total of 11 terms. If we had a power of 5, we're going to have a total of 6 terms. All right. So this is the very first question around for what we have right here. Let's try and solve the question number B. So question number B, we're supposed to find an approximate value for 14 over 15 raised to the power of 11. All right. Now, of course, I know that 14 over 15 can also be gotten in decimal form, but in a case like this, I would prefer you maintain the state of the question. The question was given in fraction, so I'll prefer you hold on to the fractional form. That may be very great for preserving the values. If you go on to change to decimal, it is very likely you would go on to hasty approximation of your decimal values, which will say a lot in your final answer. And if you look at the question you're given in question number C, you're told to find the percentage error. And when dealing with error, if you have done a lot of hasty approximation because of if you change this to decimal, it will affect the error value. That means it will add more to your error because approximations, don't forget, the approximation generally will produce an error. So if you were approximating all the fractional values also, it will add to the error. So the possibility of you getting this percentage error perfectly in line with whatever the real answer was may not be there. So you have to try as much as possible to preserve the fractional form. All right, so trying to solve the approximate value for 14 over 15 raised to power 11. Of course, don't forget, you can see right here that we have 11, we have 11. That's the basis for you being able to make use of linear approximation. All right, so what do we do next? Again, it's the same thing. You have to ask yourself, what will be x for you to turn 1 minus 2x to 14 over 15? What should be your x value that will make 1 minus 2x equals to 14 over 15? So there's no need to rack your brain around that. Just solve it as a mathematical argument. So all you have to tell yourself is 1 minus 2x being equals to 14 over 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. 15. So we try and solve this. Obviously, you can. I always love to change to wherever I see the negative sign, I want to take it away because I love to solve with positive values. Of course, in the case where I can do that. So I will change this minus 2x to this side and bring in 14 over 15 to this side, just so that I have, why not, since it's something I could do. So it's not, you can do it anyhow you want to do it as long as you get the same answer. All right. So what we have here, if you do 1 minus 14 over 15, of course, you know that a simple way of solving fractions, I believe you should know this. I can decide to change 1 to 15 over 15, and I can change this to 14 over, of course, this is 14 over 15 there. 15 over 15 is 1, so I'm just doing this so that I will have a uh, very straight way of doing my LCM, all right? So solving this now, I can easily get my LCM to be 15, and I can have 15 minus 14, all right? So this will be 1 over 15 equals to 2x. Don't forget, I was not told to find 2x, I was told to find x. So I still have to go on to um, solve for x. So how you want to do that is up to you. You can decide to cross multiply first. You can decide to divide both sides by 2. But whatever you are doing, just do it perfectly well. So if I'm cross multiplying, of course, this will be uh, 30x equals to 1, because 15 times 2x is 30x, 1 times 1, then I can have my x here equals to 1 over 30. All right. And if I decided not to go through that route, you can go on to divide at this stage, divide both sides by 2. That'll be 1 over 15 divided by 2 equals to x. That'll be 1 over 15 times 1 over 2. That'll be x. And then x here is also still 1 over 30. So whichever route you decide to follow, my x value is the same, 1 over 30. All right. So getting my value of x being 1 over 30 is a major landmark in achieving my final answer. So what I have to do next now is to fix in the value of x as 1 over 30 into my expression. That will give me the approximate value for 14 over 15 raised to power 11. All right. All right. So what we have right here is 14 over 15 raised to power 11 will be equals to 1 minus, you have 22. We have 1 over 30. We have 220. We have 1 over 30. So you just go on to fix in your value of x as 1 over 30. Right? So you go on to make these calculations, and you're supposed to arrive at something of this form. Of course, 22 over 30, you'll be having 11 over 15. You go on to solve this, you'll be having 11 over 45. And this will be 11 over 225. And this will be 22 over 3375. So the approximate value that this is going to give you, this will give you an approximate value of 1582 over 3375. So this is the approximate value for 14 over 15 raised to power 11. This is it right here. All right. Good. So we have to go on now to try and solve for the percentage error, which is the very last question we have in this question. All right. So, but for you to get your percentage error, you have to also get your error first. All right. All right. So the percentage error is given as this, of course, the actual error, which is very important, over the true value. Now you have to put in an absolute value here because, as I told you earlier, you do not want to be concerned about the sign. So depending on the values, on how the values go, you don't want to have a negative answer because you're not concerned about the sign when dealing with error. So now, of course, I'm sure you recognize that the error, the actual error, which is the same thing as the error, we can say it's the true value minus the approximate value. We did this in the previous question. So now what we want to do is to go on to bring in our values. To get the true value, we will have 14 over 15 raised to power 11. We have to press this on a calculator. That's how to get the true value. So you subtract this from the approximate value, which is what we got here, 1582 over 3375. Now let me say this. Sometimes this may come before this. It's not something that you, it doesn't mean nothing if you have it as approximate minus true or true minus approximate, but just for the sake of following a pattern, that's why I'm making it true minus approximate. But some people may actually make it approximate minus true, and that's the reason why we have the absolute value here. So whichever one you do, all you're looking for in terms of the error is the distance from each other. That means the distance that the approximate value was from the true value. That's all. We're not interested in if it's a positive distance or a negative distance. If it's bigger than the true value or it's lesser than the true value, it's not what matters. All that matters when dealing with error is how far was it from the true value. That's all that matters. All right. So fix this up here. The true value obviously will be what you press on your calculator, and then you have your absolute value times 100%. All right. So this is how you solve for your percentage error. So if you go on to press all this on a calculator, you should arrive at a final answer of 0.122 percentage. All right. So that'll be all for this particular question. And we have one more question before the end of this video. A very, very important question. It comes with a different dynamics. So stay tuned, please, for the next question. All right. So this particular question comes with a different dynamics. You can see the difference here is that we have two different variables. So we have the variable x and we have the variable y being present. So you can see that in this particular question, we have something new. Of course, you have to follow the same process, and you would not get a wrong answer by following the same process. So let's take a look at how to solve this. Of course, the very first question wanted us to obtain the binomial expansion of x plus 3y raised to power 6. So if you follow the right procedure, x plus 3y raised to power 6 will be giving you x raised to power 6 plus 18x raised to power 5 y plus 135 x raised to power 4 y raised to power 2 plus 540 x raised to power 3 y raised to power 3. Then we have plus 1215 x raised to power 2 y raised to power 4. And then we have plus 1458 x y raised to power 5. And we have plus 729 y raised to the power 6. All right, it's the same procedure. You just have to follow it the right way. So all you did here was, in this case, you were not told to find the very first 5 terms or the first four or the first 4 terms. You are actually supposed to expand the whole thing. So the very first term, which was when your k, your incremental value, was 0, we got our x to be 6. When k was 1, we got this expression, 18x raised to the power 5y. When k was 2, we got this. So this is 0, 1, 2, 3, 4, 5. This was when k was equals to 6. All right. So this is what you're going to get for the expansion. Now, but if you're not smart, based on this particular uh, aspect, you may find it difficult to solve question number B. But I know you are very smart, so I'm sure you will be able to solve it. All right. Now, it's quite simple, but it comes with a different dynamics, as I said earlier. So we are supposed to solve 1.03 raised to the power 6. Now, looking at this expression, don't forget in our previous examples, we always said this was what we used to use to solve the second question, where we're supposed to find an approximate value. Of course, this is what the second question is saying. Or like using the expansion, evaluate this. That means we're supposed to find an approximate value for this. Now, in the previous examples we did, what we used to do was we would say, what was x that would make this expression to give me 1.03? Now, but in this case, you're having two different variables. So, what are you going to do? Because it's going to be posing like a problem. Because if you say what was x, the other question will be what was y also. So that's why I said it comes with different dynamics, right? Although it's not difficult at all. One thing you just need to do here is to observe the expression. You can see x plus 3y here. You can see 1.03 here. So you have to be very smart and understand how to express your x and how to express your y. I can change what we have here, 1.03, to be 1 plus 0.03 raised to the power 6. Of course, I've not done anything wrong. I just re-expressed 1.03. All right. Now, if I have done this successfully, obviously, I can go on to write, just for you to understand better. Imagine I wrote this first expression here. Of course, looking at this, you can see that my x now can be taken as what? 1. And looking at what we have here, I have 3y being equals to 0.03. Of course, my y here will be equals to 0.01. So can you see what I'm saying? So easily now, we have been able to get what our x value and our y value can be. So all that we have to do now to solve this particular question will be to fix in my x value as 1 and my y value as 0.01. Because if you fix x as 1 here and y as 0.01, this entire expression, which is what we're always looking for, will be equals to 1.03. So, and if that is the case, so I am permitted therefore to go on to find my final solution for 1.03 raised to the power 6 by fixing x as 1 and y as 0.01 into the main expression. So that is the whole concept of linear approximation. So we can go on now to make the substitutions. So we fix in our x as 1, and then we'll fix in our y as 0.01. Of course, just like this, that will be 1 raised to the power 6 plus 18, 1 raised to the power 5, then then we'll be having 0.01, then plus 135, 1 raised to the power 4, 0.01 raised to the power 2, and we have plus 540, 1 raised to the power 3, 0.01 raised to the power 3 also. Alright, and we have plus 1215, 1 raised to the power 2, 0.01 raised to the power 4, then plus 1458 times 1, then 0.01 raised to the power 5, then plus 729, 0.01 raised to the power 6. Right, you'll be needing your calculator in this particular place, and you would arrive at a value first that will look like 1.19405. But if you read through the question told you to evaluate this correct to 4 significant figure. All right, you need to understand the concept of significant figure, which I'm sure you do. And if you look at the significant figures here, we have 1, 2, 3, 4. So every other thing after here, we want to cut it off or make an approximation depending on what we have here. What we have here is actually 0, so we'll be permitted to change this to 1.194. All right, so this is the final value for our approximate value. All right, now in this case, we are not told to find an error, but you understand clearly that to find an error, what you have to do is just fixing this on a calculator, and just as a checkup, which I always prefer students do in an examination, when you're done with a question like this, it's always good practice for you to try and check up with your calculator. So press this on your calculator. You press this on your calculator, 1.03 raised to the power 6. What you're going to get will be 1.194052297. This was the calculator value, which we also call the true value. So, and you can see how close this is to what we got as an approximate value. So this tells me clearly already that I'm on the right track, that I'm not wrong. But imagine, for instance, you got a value of maybe 2 point something or 1.9, something that far. Of course, you know that you have made a mistake somewhere. So that's a way to check up your work. Actually, ideally, you could even check that first initially, so you are guided, right? So, but if they told you to find a error in this particular calculation, what you had to do was to just go on to make a subtraction of the true value and the approximate value. All right, guys, that will be all for this video. Now, next video, we'll be talking more on several technical questions that can be examined, that you can be examined on when it comes to linear approximation. So check the next video, word problems around binomial expansion. Thank you, guys. Bye-bye.